Welcome back, everybody. And the topic this week is a new one, and it deals essentially with the optimization problems. So for some of you who may have taken courses on machine learning or statistics or in mathematics on optimization problems, some of these topics are going to be well known, or you may have seen them before. And it's always okay to repeat some of these topics. So let me just quickly, before we move on, give you some few messages. So I sent an email about the possibility to change the lab time, since the lab time is a little bit unfortunate for many of you. I've had only one response till now, so if we don't hear anything, we will, if there are only one or two responses, we will just keep the time as it is. And the idea next week is that we are going to summarize a little bit of the activities we've had with coding. So we will spend most of next Thursday on just the lab and the project so that we see where people are. So that means that there is no lecture next Thursday, but we will have lab for 5 hours. And then the week thereafter, the week which begins with March the 6th to March the 10th, the idea is to have some more extended lectures. Eventually, we could have more lectures that specific week on March the 6th to the 10th. You probably saw the email from yesterday via Canvas. That's the only way I can communicate with you because I don't have access to your emails. And take a look at it and see if you're happy with the lab hours which we have, the schedule which we have. And then if you wish to change or the time is not very convenient, we can try to reschedule the lab sessions. But clearly this depends also on your schedules, and it may not happen that you're available at those times which we suggested. Okay, so if we now go into the topic for this specific week, so let's now look at the Jupyter notebook for this week. So we are going to look at derivatives and optimization problems, and that leads us immediately to the topic of gradient descent methods. We are going to encounter methods which many of you have probably seen in different courses. So the gradient descent, which is something which many of you have encountered, is one of these methods which is widely used in this type of calculations. And I want to give you the kind of overarching view why we do this. The other thing which I wanted to do now is also to link this tightly with project number 1. And in project number 1, we're actually dealing with a harmonic oscillator. And I'm going to go through the details with the non-interacting system because that provides a very useful benchmark for this additional element. So what is the main motivation for what we are doing now? Now, what you've seen in the previous weeks is that we have, in a very, how to say, brute force way, we have calculated the energy as a function of the variational parameters. That means that for every variational parameter, even if we are far away from the minimum, that means the optimal value of the variational parameter, we have spent the same amount of Monte Carlo cycles. This is not very efficient, because that means that if we have 100 variational parameters and we spend 1 million Monte Carlo cycles on each of them, and then just produce a grid of values and then interpolate between these points to find the minimum by some kind of minimization algorithm, where you just feed in this grid of values. That means that if we have 1 million Monte Carlo cycles and 100 values for the variational parameters, we are going to spend 10 to the 8 Monte Carlo cycles on these results. So the question is, could we actually perform the calculations for smaller number of Monte Carlo cycles when we are away from the minimum and use these values as way from the minimum to find the optimal parameters? And when we find the optimal parameters, can we then start the big Monte Carlo machinery? And this is a much more efficient way of doing things. So this is the kind of overarching motivation which we are going to look at now. So instead of wasting a lot of CPU cycles on points which are far away from the minimum, or what we might call the optimal value, we are now going to use gradient methods to run fewer Monte Carlo cycles, and with those find the minimum. And when we have the minimum, that's when we mount the large artillery and perform all the necessary cycles to get the relevant and good statistics. So this is the kind of basic overarching motivation for what we are going to do today, and also next week and the week thereafter. So, but next week we are going to mainly have lab. But what I want to do now is to build up the intuition about this by looking at what we have in project number 1 with the harmonic oscillator. And the derivations which I'm going to do now in one dimension, which are pretty simple, they apply to one particle and to many particles, which means that in your program, you can actually test this immediately because you will have analytical expressions for the integrals we are going to deal with. And then you can check your numerical evaluation against the analytical results. And that's extremely useful. So I'm going to step you through these elements just to look at the expressions which we have to program. So we take this kind of top-down approach first. And then when we've done that, we are going back to different gradient methods. There is also a set of tricks, lots of tricks in these gradient methods. And for those of you who are going to opt for the machine learning variant of this project as project 2, there is a method which has been widely used in neural networks with Monte Carlo calculations, which is called stochastic reconfiguration. And that's something which is going to be relevant for us when we look at project 2, and in particular for those of you who are interested in the machine learning variant of this specific project. So the machine learning variant means that you, as a variant for project 2, means that you replace the trial wave function, which we have here, with a neural network. And you'll be surprised to see how fantastic the results are. So I'm totally addicted to this approach. I should just confess that. So I've been doing many body physics for soon 40 years, and replacing the trial wave function with a neural network is perhaps some of the best things I've ever done in my life. Okay, so let's now go back to the, one of the funniest things I've done. But let's go back to the technicalities which we have to deal with this week. And I'm going to step you slowly through the different details and the kind of equations which we need to plug in. So if we now stay with the project 1, and in project 1, what we have been doing till now is essentially to look at the non-interacting case. Where did my screen end? There we are. Okay. So we are now going to look at the optimization case, and the typical situation where we now calculate the energy as a function of these variation parameters. And now I'm just going to look at the one-dimensional case. So I'm plotting the energy as a function of the variational parameter. And the typical energy is going to look something like this. And you've probably seen that already. We saw that in the very first encounter. And it means that we are going to have an alpha optimal, which I'm going to simply write as an alpha hat here. So when you see this hat symbol, that means that this is the value which we are going to look after. What we have done till now is actually to produce a grid of values, the whole series, and each of these values which we have produced, like alpha 0, alpha 1, alpha 2, etc., all the way up to some value here, some alpha of n. These values here, they produce energies which are evaluated with the same number of Monte Carlo cycles. So as I mentioned in the very introduction today, if you now have 1 million Monte Carlo cycles for each of these points, and you produce hundreds of these points, you end up with something like 10 to the 8th or 10 to the 9th Monte Carlo cycles. Whereas in principle, what you could get away with is just some few cycles here. So you could now think of you calculating the gradient, finding the slope, So if we now look at this equation here, where the energy is given by this parameter alpha. So let me just rewrite some of these equations. So I'm going to use a notation now, which is more physics-like. So this quantity here, this is the expectation value of the local energy as a function of this parameter alpha. And now we have only one parameter. And this is given by the more physics-like notation, which many of you are familiar with. And we have rewritten this as an integral. And now we are going to just stay in one dimension. So the one-dimensional case is the one which we are going to elaborate here. But then this is easy to generalize to more dimensions. This is then given by P. This is a probability as a function of alpha and multiplied with this local energy as a function of alpha and x. So this is the integral which we are evaluating. And what we're interested in now is actually the expectation value of the derivative of this quantity E of L. And we want to have this one equal to 0, and that's going to give us the optimal value. So that means that what we want now is this alpha hat, which is given by a minimization problem. And for all the alpha defined in terms of these real parameters, and if we have n of them, we have, like in this specific case, we have a set of parameters, alpha 0, alpha 1, and etc. And this is going to be given by the minimization of the expectation value of the local energy. So what we need now is to calculate derivatives. When we have more than one set of parameters, so suppose we have a 10-dimensional parameter space, so we can have parameters alphas, betas, etc., then clearly this derivative is going to be replaced by the gradient of the expectation value of the energy. So in general, what we need the gradient of this expectation value of the local energy as a function of many such values alpha. And we want this one set to 0. Now, what we are going to use now, when we go back to the image which you see here, is that we are going to calculate these gradients, and we are going to use these gradients to step down to the final value. And these gradients are going to be calculated with fewer Monte Carlo cycles than the cycles we are willing to spend at the optimal point. So the whole philosophy now is that we are going to calculate gradients. So I'm going to write these gradients like a delta of the expectation value of the energy and a skip alpha with fewer cycles. And with the gradients, we are hoping now that we can approach this optimal value. Now, the problem you will see here is that these gradients are given by integrals, which are determined statistically. So we are using stochastic methods to evaluate these integrals. And this will take place whether you're doing machine learning methods, or whether you're doing standard Monte Carlo methods, or you do diffusion Monte Carlo, etc., etc. So the evaluation of these integrals are going to carry a statistical error themselves. And this is also going to be the bottleneck of the calculations. However, the idea is to save CPU cycles, because if you have a multidimensional energy functional, this clearly you would need tons of Monte Carlo cycles for every point, and to evaluate the minimum for all these grids of points is something which is going to take a lot of CPU cycles if you want the same level of accuracy for every single point. So the overarching idea now is to try to use some gradient method to go as quickly as possible down to the optimal value alpha. And then when we have this optimal value alpha, that's where we are going to run the big Monte Carlo calculation. Okay, so let's now look at the technicalities, which we need to plug into the code. So the question now is, what do we have to code? So there are two basic elements, and we are going to go through the basic elements. So the first element which we need is actually the gradient of this expectation value of the local energy. So there's no way we can escape that quantity. The second thing which we need is a method to find the optimal minimum. And that leads us to gradient descent methods and a whole family of these type of methods. And you will be surprised that again, and for those of you who've taken a course, let's say in machine learning or optimization problems, you will see that the basic starting point is Newton's method, or what we normally call Newton-Raphson's method. And everything which we're going to deal with are going to be permutations or perturbations of Newton-Raphson's method. So the basic method is what is called Newton-Raphson, which we are going to derive for these specific cases. And this has a plethora of methods. So one is just a standard gradient descent. Gradient descent. Many of you have encountered things like stochastic gradient descent. And I'm going to use a shorthand, GD. This acronym stands for gradient descent. So stochastic gradient descent. There are other methods like steepest descent, which is also a method which is easy to implement. But you will see that all these methods are going to rely on you being able to calculate the second derivative of the expectation value of the energy. That second derivative is going to be proportional to the variance of the energy. However, to calculate the variance is going to involve 6 to 7 multidimensional integrals. So we don't want to evaluate that quantity. That quantity defines also something which is called the Hessian matrix, and some of you may be familiar with that. You may have heard about this in studies of convex optimization theories. So we have a steepest descent. We have other methods which are called the conjugate gradient descent, conjugate GD, which we're also going to look at. But we will most likely just implement some kind of variant of the gradient descent. And then we have pseudo Newton methods, which we're going to discuss, and which are often widely used, pseudo Newton methods, which actually try to estimate the second derivative and uses that second derivative approximatively. And when you look at stochastic gradient descent and gradient descent and so on, what you then do is that you typically replace the second derivative with a parameter, which in machine learning is called the learning rate. And this parameter pops up here again as well. So this is a rich field in which at certain points you have to make some compromises. And the compromise here is typically that you don't want to calculate the second derivative. You will see now that when we calculate the gradient, this in itself is already going to lead to 3 integrals, which we have to evaluate stochastically. So the complications you get if you want to calculate the second derivative, that's going to lead to even more integrals to evaluate. But let's go carefully through these steps. And let's look at the project number 1 as an example and starting point. And this is relevant because you will have to program this anyway. So the tests I'm going to set up now are things which you can implement easily in your code. So project 1, without the interaction piece, because now we can calculate the integrals analytically without the two-body interaction. So this is what we are going to look at now. And look at the equations which we will need to code and how we can test that what we have coded is correct. So if we look at the project here, if we now think of one particle In our case, these are bosons in one dimension, and there is no problem in extending this to many dimensions, or 3 dimensions at least, and many particles, because it's a non-interacting case. So we have a trial wave function in this case, which is given as a function of x and only one parameter alpha. So there are no vectors on the symbols here. And this is given by minus 1/2 of this parameter alpha squared and x squared. And just to quickly remind you of what we have. So we have a local energy as a function of x and alpha, which is then given by 1 divided by this trial wave function. We have a Hamiltonian times this trial wave function. The Hamiltonian for that specific case without an interaction. And when we only have one particle, and since we are in one dimension, it's given by h bar squared divided by 2 times the mass, d of dx, and then plus the harmonic oscillator constant multiplied with x squared. So this is the Hamiltonian. And what we have done is actually to put h equal to m equal to the speed of light equal to the electric charge, and we put all these constants equal to 1. Now we have to be a little bit careful here, and because this constant k, if we put this constant k equal to 1, then we're actually putting a constraint on the oscillator energy. So let me rewind a little bit how this parameter alpha comes in the calculations which we have. So let's take a closer look at this alpha, because that's going to be intimately linked with this parameter k here. So let's see how that parameter alpha comes in with respect to the value of k. So if you go back to the standard discussions of the harmonic oscillator, what we normally have is a natural frequency, which is given by k divided by m. So that's the standard approach in a classical harmonic oscillator. And that means that this omega squared is obviously k divided by m. And we know that the energy of the system, when we have this oscillator frequency in one dimension, is given by h bar times omega 0 times nx plus 1/2. If you're in 2 dimensions, it's 1, and if it's 3, it's 3/2. So we put h bar equal to 1, but we have to be a little bit careful with the omega 0. So let's just remind ourselves a little bit about the harmonic oscillator case. So if you now look at the Schrödinger equation for the harmonic oscillator, so what we have in one dimension, and this argument can easily be extended to higher dimensions. So we have a d of x. So the way this parameter alpha appears is through the following analysis. So I have this k of x squared, and this is multiplied with the wave function, and this is again equal to the energy times the wave function. Now this parameter k is in the harmonic oscillator given by m times this frequency omega squared equal to 0. So what we normally do then, when we are preparing these solutions, is that we introduce a dimensionless coordinate, so which we can call for rho, and that is just given by a scaling with x divided by a parameter alpha. So this alpha which we have is actually a scaling parameter. So x has dimension length, alpha has dimension length. So when I plug in this alpha into my equations, what I get now is minus h squared divided by 2m alpha squared, and then I have a d. So my operator now changes, and then I have plus 1/2, and then I have m of omega squared times this alpha squared times rho squared, and then I have times the energy times the wave function, and that's equal to the energy times psi. Now I can scale the equation so that I get rid of these constants. So I multiply with m times alpha divided by h bar squared. So till now I haven't set h bar squared equal to 1. So if we do that, then we get the following equation. We get minus a half, and then we have a d of d rho squared, and then I have a plus 1/2, and now I have m squared omega squared alpha to the power of 4th divided by h bar multiplied with rho squared, and then this is psi, and then there is a new energy which I just called for energy prime, which now contains m times alpha squared divided by h squared, like that. And in this type of calculations, what is common then is simply to say that since alpha is a constant which I have plugged in to make the distance to be a dimensionless quantity, so rho is dimensionless, I can actually choose this alpha as I want, and I can choose to set it equal to 1. So if I do that, that means that alpha is going to be given by the square root of h bar divided by m and omega 0. And you can check that you have the right dimensionalities here, because alpha should have a dimension length. So if I look at the dimension, this is this kind of strange notation. So this has dimension length. And you can see that in this equation here, if you now look at h bar and you multiply with h bar on nc squared and divided by mc squared times h times omega 0, then this quantity has dimension energy. This quantity here has dimension energy. And what you have in the numerator is energy squared times length squared. That's the dimensionality of what you have there. So the energies cancel each other, and you take the square root of length squared, which gives you length. So the dimensionality of alpha is length. Now, what you have to be careful with now is clearly that if we put omega 0 equal to 1, and then we put that one equal to h, equal to m, equal to c, equal to e, etc., all the natural constants, then we have already opted for an energy which now is going to be given by E and x equal to nx plus 1/2 in one dimension. However, if you change omega 0, that is going to change your alpha parameter. So you have to be careful now if you change frequency. So the frequency defines the extension of your trap, the harmonic oscillator trap. And clearly changing the frequency means that you also have to be a little bit careful here. Okay, so if we now look at the harmonic oscillator case we have here, what we are doing is actually to calculate the local energy. So if I take this trial wave function, let me just repeat it, of x of alpha, which is equal to e to the minus 1/2 of alpha squared times x squared. What I have now is a probability of x of alpha, which is the wave function squared. So this is e to the minus alpha squared of x divided by an integral over d of x of e to minus alpha squared. So that's the probability we have defined. And then I have a local energy, which is now simply given by this 1 over psi of t. And now I'm going to be a little bit sloppy with the x and the alpha dependence. And this has a Hamiltonian which acts on this psi of t. So these are the local energies and the probabilities which we have. So in this particular case, we can now actually calculate the expectation, the local energy. Is pretty easy to set it up. So if we look at the equation for the local energy, what we end up with then, so let me just find my notes here. So this E of L, when we plug it in, and this is something which we did in the very beginning of the semester, this is simply given by 1/2 times alpha squared plus x squared, or 1 minus alpha to the power of 4. So that's the local energy. And it means that the expectation value of the energy, which we wrote down in this specific way, so we are integrating away x. This is simply d of x of p of x function of alpha multiplied with the EL of x of alpha. This has an analytical answer, and it's not that difficult to perform the integration. So that gives us, when we calculate it, alpha squared plus 1 over alpha cubed. And then, when we want to take the derivative of this quantity, and this is actually what we are going to do now, this is going to be given, we want this to be 0. So this is going to be equal to 1/2 times alpha minus 1 divided by 2 alpha cubed, and this is equal to 0. And that leads to alpha equal to 1, as you have seen in your codes. But keep in mind now that this alpha depends on you having set the harmonic oscillator frequency to 1. So if you have another value for the harmonic oscillator frequency, you have to be a little bit careful here, because that will change your minimum of the energy. Just keep that in mind. So when we made this calculations here, we have made a simplification where we put omega 0 equal to 1. Now, this quantity here can also be used to calculate the second derivative. So it's easy now because we have an analytical expression. So if we take the second derivative of the local energy with respect to the parameters alpha, we are going to see that this is equal to 1 divided by 2 plus 3 divided by 2 alpha 4. And alpha is assumed to be a real constant. And that means that in this specific case, this is always going to be larger than 0. And alpha is assumed to be a constant which is larger than 0 and real. So this means that this is obviously a convex problem. So this is a convex optimization problem. So we have an energy minimum. And most of the physics energy functionals you will encounter, or basically all of them, I've never encountered a physics energy functional which is not a convex function. So, but there may be local minima, and we could be stuck in local minima, and that's something which we don't want. So the thing we need to do now is actually to find the equation based on these integrals. So our problem is actually that we are evaluating in general for many particles. We're actually calculating this expectation value here as a multidimensional object in terms of the alphas. And this is given by an integral over d of r, where r is now a variable which contains the coordinates of all particles. And then we have p of r and multiply with its local energy, which is now a multidimensional object. So we have to evaluate multidimensional integrals. So the case which you see here, this simple case, is extremely useful now when we're going to set up the integrals. So you can actually test this for one or many particles in a non-interacting case for the harmonic oscillator. So this is the kind of benefit of this simple system which we have here. And the results are going to be for many particles. It's just going to be the single particle result scaled or multiplied with the number of particles. There is no difference there. So we have a very simple test which we can now use to set up the equations. So let's now look at the derivative of or the gradient. So let's find the expression which we need to code for the gradient as a function of these variational parameters. So this is the gradient with respect to the variational parameters. And obviously we want to drive this one to 0. So let's look more closely at the expressions which we have. So what we are going to do now is to specialize to the harmonic oscillator case which we have, to our project 1 case without an interaction. And then you're going to see from the algebra here what the equations are going to look like in the general case. So it's easy to go from this case to the general case. So what we need to evaluate now is in the one-dimensional case, so one dim and one particle. What we have to evaluate is this d of EL of d alpha of d alpha, and then we have this integral over d of x and p of x and alpha, and then EL of x and alpha. So clearly, since alpha is independent from x, we can then rewrite this one as an integral over d of x. And then we have to evaluate dp. Now I'm going to skip the dependencies of x and alpha in these equations, times E of L plus the probability and multiplied with the derivative of the local energy with respect to alpha. So let's see let's look at the evaluation of this quantity here, where we now have assumed that this probability of x of alpha is the function which we have. So this is just a wave function squared. So instead of a half, we have obviously squared it. So we get rid of the factor of a half. And then we have in the denominator d of x of e to the minus alpha of x squared. And in the notation here, I'm just going to call this for a normalization constant. So I'm just going to call this one n. So let's look at the first term. The second term is going to give us exactly the same answer. So I'm going to do the first term here, and then I'll leave it to you as a small exercise to take the second term. So it's pretty straightforward. They're going to give the same result. So what I'm going to have now, if I look at dp of d alpha, if I plug that in and multiply with E of L, so let's look at this specific term here. What we are going to get then, and we take the integral of d of x. So we are going to get the following expression here. So we have d of x. So let me see if I can squeeze everything in properly here. And then we have the derivative of the wave function. So the first term, we have to take the derivative there. So we get a 2 alpha of x of e to the minus alpha of x squared. And this is then multiplied with EL. And we have to keep in mind that we are using just the standard rules for derivatives of a numerator and a denominator. So this is going to carry a term which goes like n here. And this has so we are going to get a term n and divided by n. And then we have an E of L. That's the local energy. And this depends on x and alpha. And then we get a new term, which is going to be given by e to the minus alpha x squared multiplied with the local energy divided by n, the normalization constant. And then I have an integral. So what I get then is a d of x, and then I have minus 2 alpha squared of x of e to minus alpha. So I'm going to put primes on these because they are not, these are other integration variables. So alpha squared of x prime squared. And this is then multiplied, no, sorry, it's divided with n. So this is the expression which I get. Now, if you look a little bit carefully at what you have now, so this term here returns just a number. So this in itself is an expectation value. And we are integrating out x here. So that just returns a number. Then, if you look at the expression which you have here, this one, if you look carefully at that one, so let's ring this out. So we have the details in here. So if I take this term here, this one is nothing but P, the probability, x of alpha, multiplied with the local energy of x and alpha. Okay? Because the first term e to the minus alpha x, alpha squared x squared divided by n, that's nothing but our definition of the probability. And then we multiply with E of L. And you see now that we also have this integral over x here. And this is just multiplied with a constant. So if we look a little bit more carefully at what we have here, so let's look at this term. This is a term, if you now look at it, it's going to contain this n, which is the norm used in order to define the probability. But I could actually rewrite this term, which you see here, as the wave function squared. But if you look carefully here, you can actually rewrite this term, which you have here, this whole term here. This is nothing but the probability, and I'm going to write it like this, the probability of the wave function, the trial wave function, derivative with respect to alpha, divided by the wave function itself. So keep in mind that what you have here is actually the derivative of the wave function, this term here. So that gives you this one. And then if I now look at the second term, which I have here, this is now part of a probability. And I can actually rewrite that one in terms of 1 over psi of t, and then this becomes an expectation value. So if you look more carefully, if you look at this term here, that specific term, so let me just see that you are a little bit in doubt here, this minus 2 alpha squared of x prime, this is nothing but the derivative of d psi of t of d alpha divided by the wave function itself. And you see that if you plug in the wave function here, because we have a d of e to the minus 1/2 in this specific case, and then we have an alpha squared x squared divided by this d of alpha, like this. And then this quantity here gives us now alpha squared times a factor of 2 divided by 2. So this parameter of 2 is something which we're going to collect a little bit later when we sum up everything. But you can actually rewrite that one. This is going to have a factor of 2 in front here, which we are going to keep a little bit later. So if we just take away this factor here, this one, so we just rewrite it like that. That is just the wave function, the derivative of the wave function, divided by psi of t. And if you now look at this one, this quantity here, that is going to give us alpha squared times x of e to the minus alpha squared of x squared. And if I divide with the wave function again, 1/2 here, if I divide with the wave function, this disappears. And then I'm just left with this term here, which is the term I would have in here. And then the rest here is just this term divided by n, which is our probability. So that's the expectation value of that quantity. And what I'm going to do next now is to collect these terms of 2, and you will see that due to the hermeticity of the Hamiltonian and the wave functions, we can actually rewrite the term which you see here. This is something which we can now rewrite as 2 times, and the first term is going to be the expectation value of the derivative of the wave function with respect to alpha divided by the wave function itself, multiplied with the local energy, minus an expectation value of d psi t d alpha. So this is an expectation value by itself, which we have to evaluate as an integral, and multiplied with the expectation value of the energy, which we have already done. So what you see now is that we have 3 integrals. And we have an integral which now contains the derivative of the wave function divided by the wave function itself, multiplied with the local energy. So this is one integral we have to evaluate. We have this integral over the derivative of the wave function times the integral which we have already evaluated. So you see, we are getting now, in order to calculate the derivative, we are actually getting 3 integrals to evaluate. One which were done before, and then we have 2 new ones. Now, there is a simplification you can do now, because if you look at d psi of t of d alpha divided by psi of t, this is something which we can evaluate in a more efficient way as the log of psi of t with respect to alpha. Because that expression which you have is nothing but the derivative of the log of a function. And our wave functions are typically given by, so psi of t is typically given by some e to the minus or some exponential as a function of some specific function f. That's a general form of the wave function which we have. So clearly taking the log of this exponential simply gives us a derivative of a function of f. So that means that what we end up with then is to calculate df with respect to this parameter alpha. And that is a much simpler equation to evaluate numerically. So just keep that in mind. So the general expression, which you can easily extend based on what we have here, is an expression which is given in terms of these integrals here. So that's what we need to program. Any questions so far? Before we take a break, I went just a little bit over time here, but I wanted to give you the equations which we need to evaluate. And I simply started with the simple wave function which we have in project 1, because this is going to allow us to make tests in the project when we now implement the optimization part. And the optimization part is needed because else you're going to waste tons of cycles and your code will be inefficient. So in order to have a professional Monte Carlo program, you will actually need to add these elements. So we've been adding Metropolis algorithm, we've done importance sampling, and now we have the next step, which is an efficient optimization of the parameters so that we can plug in the big calculation at the optimal values of the parameters instead of wasting CPU cycles on setting up a grid where every point in the grid has been evaluated with the same number of Monte Carlo cycles. So if you can get away with, let's say, 1/10 of the cycles in order to do the gradient descent, and then you can plug in millions of cycles in the statistics of the final expectation value based on the optimal parameters, then that really saves your day when it comes to number of cycles. So this is the overarching motivation. And the equations we have to program are these equations which you see here. This one, sorry, this equation here, and this equation here. So after the break, I'm going to show you how you can implement it with these codes which we have been discussing. And we are then, when we have implemented it, that shows you what you should do in project number 1. And when we're done with that, we are going to dive into the gradient methods and what kind of methods will be useful to study in these evaluations. Does that sound like a plan, guys? So I hope it's pretty transparent. We have a new task, and that is to start thinking of encoding these expressions here. And when we are done with that, the next thing which we will need to plug in, since we are doing a stochastic evaluation of an integral, we want to evaluate the standard deviation in as reliable way as possible. And as reliable way as possible without having to mount an infinity of Monte Carlo calculations means resampling techniques. So for those of you who have encountered things like the bootstrap method or blocking methods in earlier courses, you're going to see them again. So gradually then, at the end, with parallelization, you will have a professional code, and essentially with the same elements as any professional codes you will find in the literature. Okay, I went a little bit over time, so I hope it's okay if we just meet at 3:20, 20 past the hour, if that's okay. And then we just stretch the recording. So the equations which we need to program are the equations which you see here. And the whole thing now is about how do we evaluate these integrals in the most efficient way, and how do we actually calculate these gradients, and how do we use these gradients. And this is what it is about in the next coming minutes. And the first thing we are going to look at now is a simple implementation of this for this 2-electron case, which I've been using as an example in the Jupyter notebooks and the lecture notes. So let's go back to the Jupyter notebook then and take a quick look at that. So if you scroll down in the lecture notes, what you will find is a simple program. So basically what you see here is a kind of repeat of what we have. And you will find a summary of the equations which we need to set up. And I leave it as a kind of exercise to show that this is the case. I gave you the basic elements for the special case, which we have for the harmonic oscillator expression. And if you want a real challenge, is to find the corresponding expression for the variance. And you will see that's going to be a nasty equation. And as we will see later, the variance is going to be linked with the second derivative of the energy with respect to this parameter alpha. And that variance is a quantity which we would not like to evaluate for general wave functions and multidimensional functions. But what you have here is a simple Python program where I've just extended the program which we discussed last week and the week before, etc., etc. So what you have is an interacting case where we have a Coulomb interaction and a harmonic oscillator. So this is a model for 2 electrons in 2 dimensions interacting in a so-called quantum dot system. And there is a harmonic oscillator piece, which would now be given by R1 and R2. And you can see that you have the variational parameter alpha here, which multiplies the harmonic oscillator piece. So if you want to use this program and compare that with your programs, the only thing you need to take away are these R1, 2 and these denominators and this parameter beta. You don't need that one. And then you would simply keep the standard harmonic oscillator. That means also that the energy which you see here does not include these terms here, which then translates into what you see here. So these additional terms which you see here, they come from a correlated part of the wave function, which we discussed in previous weeks and is normally called a Padé-Jastrow correlated factor. Now, the next thing which I do now is I calculate analytically the derivatives. So I'm calculating the derivative of the wave function, not the energy, but the derivative of the wave function. And in this particular case, what I have now are these analytical derivatives for the the correlated part of the wave function, and 2 here, this is just the plain harmonic oscillator part. And if you remember from what we had, I put this parameter, the parameter alpha, as a variational parameter, and that is linked with the value for the harmonic oscillator frequency. So in this case, I'm just setting up this derivative, and I'm setting up the same thing for the quantum force. So you can actually take away the derivative of the correlated part of the wave function if you want to use this code in order to compare that with your code. So what I'm doing here now is a not a very strong Monte Carlo sampling. I just take 10,000 integration points. And what I'm using this for is to calculate to find the optimal variational parameters. And in this case, what I'm doing here is simply to run through the same program, but now I'm calculating the total derivative of the energy. I need my local energy. I need the expectation value of the derivative of the wave function. And I need the expectation value of the wave function derivative times the energy. So I have 3 integrals which I need to evaluate. And that clearly is something which is going to complicate a little bit my calculations. I do the same things as before. I have my Metropolis Hastings part. I move particles. I test whether I accept the move or not. And then when I've done that, I update the different quantities. So here I update the local energy, contribution to the expectation value of the energy. That's one of the integrals. I calculate the derivative of the wave function, which is this log of the wave function, the derivative of that one, when we are going to look at things in a more efficient way. And then I have the next term, which is the delta psi term. So I'm going to get a term here, which I'm going to multiply with the energy. So I have this derivative of the wave function times the energy, which is now given by this derivative of the wave function with respect to parameters alpha and the local energy delta E. And then you see now that the energy derivative, the total energy derivative, which I'm returning, is now given by 2 times this derivative of the wave function times the energy, this expectation value, times the expectation value of delta psi, times the expectation value of the energy. So this is the way I'm encoding these 3 integrals. So anything which you can cook up, which can improve this type of calculations is most welcome. And you see here, I have a number of particles, 2, dimension 2. I have a guess for the variational parameters, which are close to what I've seen from other types of simulations. So I'm giving a guess here. It could be a random guess, or it could be a guess which is more based on what you expect. And I calculate the derivatives. I do a very brute force gradient descent calculation. And as you will see here, I'm just setting up 50 iterations. And with 50 iterations, this energy has not yet converged. Now, the thing is, in this particular case, which we have here, since we only have 2 parameters, and you guys are going to have only 1 parameter when you're going to optimize the bosonic wave function for many bosons. That means that in principle, one could think of perhaps calculating the so-called Hessian matrix. The only problem then is that the Hessian matrix is going to be proportional to the second derivative of the energy. And that means that you will have to evaluate 7, I think it's 7 integrals stochastically. So even if we only have 1 parameter, the evaluation of the quantities which we need for the second derivative are extremely CPU intensive and lead to statistical errors, which sometimes can be large because we have we are not willing to spend that many Monte Carlo cycles in calculating them. So here I'm actually doing the simplest brute force gradient descent method, where I actually have a parameter which replaces now the second derivatives. And this parameter is a parameter I call for eta. And I simply multiply that with the gradients. That updates my value alpha, my value beta. And you can see now that after 50 iterations, this is the energy I get. The exact value is 3.0. This is the optimal value of alpha. It's actually close to 1. And this is the optimal value of beta here. But you see now that the derivative of the energy with respect to alpha is not 0. And the derivative of the energy with respect to beta is also not 0. So these are the gradients after 50 iterations. Ideally, we would like to have these gradients as small as possible. So the kind of test which I'm recommending you to do when you implement this now is actually to run these calculations for the non-interacting case. And for the non-interacting case, you will just have 1 parameter alpha. And since you have also analytical expressions for the derivatives, you can then test your numerical evaluation of the integrals against the analytical expressions. And you can then see how many iterations you would typically need in order for the derivatives, or the gradients in that case, to be equal to 0. Now there's something more which we're going to discuss, and that is a ready-made function which is called Broyden's algorithm. It's actually called Broyden, Fletcher, Goldhaber, and I never remember the name of the the author which begins with an S. So this is something which is a so-called quasi-Newton method, which can be implemented easily using SciPy. So the only thing you need to give them to SciPy is the function which you see here is the same as the one before. And we calculate these expectations values stochastically. But what you need now is a calculation of, you need a function which sets up the derivatives, as you can see here. So this calculates the energy derivatives. So this function from SciPy, which implements this Broyden's algorithm, needs a function for the derivative as a function of the variational parameters, which are given by this x0. And it needs a function for the function itself, which in our case is the expectation value of the energy. So in this particular case, we actually, we have to feed in order to use that function, two different functions. And in both cases, we are calculating the energies and the derivatives. So this function, which is called minimize, that's a functionality in SciPy, requires a method. And in this case, I give this Broyden's method, which we are going to discuss in more detail, not next week, but the week thereafter. I need to give the energy derivative. I obviously have the energy here, and x0 are my variational parameter, where I give an array in terms of 0, x alpha given by 0.9 and beta equal to 0.2. So this is also something which you could implement very easily in your code as soon as you have an expression for the energy derivative. And in this specific case, actually, it needs only 4 iterations. You can see now with the tolerance which I've given, 10 to the minus 4, it has a default value of iterations, and it has not received the precision which I put in here. But it needed only 4 iterations, and this is a number of function evaluations, and it gives me parameters here. Remember now that these integrals are evaluated stochastically. So every one of these integrals, the integral for the energies has 10,000 Monte Carlo cycles, and the energy for the integrals for the energy derivatives has also 10,000 cycles. So clearly increasing the number of Monte Carlo cycles here can be beneficial for the search of the optimal values. But this method finds now a set of parameters which is not that different from the one which my brute force method gave. And then what we have is now an expectation value for the energy, which is close to 3.0. We don't evaluate the standard deviation here. This is a topic by itself, which we will discuss in more detail when it comes to the implementation of a method which is called the blocking method. So what you have here now is a starting point for running your advanced Monte Carlo scheme, where you then would have simply to start your calculation with these parameters, and then you would run with as many Monte Carlo cycles which you deem appropriate. So this is the kind of overarching picture which we want to give you. And the next topic which we are going to look at now is actually the discussion of these different ways to calculate the gradients and find the optimal variational parameters. That means driving the gradients to 0. And when we have that, or to whatever way we define 0, when we have that, we are then going to mount the large Monte Carlo calculations. Now, feel free to ask questions before we change gears a little bit. I mean, if something is unclear, have questions about other technicalities. And then if not, we are just going to move over to the discussion of these various methods for finding the zeros of a wave function, no, of the energy. No questions till now?
I have one quick question. What was the number of iterations when you didn't use Broyden's method? Do you compute that?
I just fixed it to 50.
Oh, okay.
So that was just a brute force. I didn't have any if test in the code whether I should stop when the derivatives are smaller than a specific values or the energy doesn't change by a specific value. So typically what you would do now is that you, if you look at the parameters you have, these alpha and beta in my case, one of the tests you would typically do is that if these parameters don't change by a fixed amount, then you would stop the iteration. Because often it will be difficult to get the gradient get exactly to zero. So
I was wondering, like, if for the same precision that you achieved for Broyden's method, if it would require less or more iterations than the previous implementation.
So my case, so Broyden's method is actually an intelligent way of estimating the Hessian matrix in this iterative procedure. In our case, since we have two parameters only, this Hessian matrix is going to be a 2x2 matrix. In your case, it's just going to be a one-dimensional object because you have only one parameter alpha. So life is even simpler. And I recommend actually to do everything for the harmonic oscillator without any interaction first, because then you know that your machinery is functioning. Okay, so what I wanted to do now is actually start this discussion about the different gradient methods. And that means that we're going to start with Newton's method, which is the simplest possible one. And basically all these methods are kinds of iterations based on Newton's method. And let me now just bring that up. So let me just bring the whiteboard back again. Okay, so what we need now is a discussion of what we normally call the optimization methods, which essentially translates into gradient methods, optimization methods. Also known as gradient methods. So what we want is the gradient of the energy with respect to the set of parameters alpha, and then putting vectors to indicate that alpha does not need to be given just by one scalar, but it normally is a set of variational parameters. And we want to calculate the derivatives of the expectation value of the energy with respect to these parameters. And obviously we want to drive this to zero. So this is a function which we want to optimize. So in principle now, suppose that we have an iterative procedure, we can now set up a Taylor expansion. So let me just give you the basic mathematics of what is normally called Newton-Raphson's methods, which is based on a Taylor expansion. So we Taylor expand this E of L of alpha, this expectation value, which we have here. And I'm going to introduce a notation which is more compact. So I'm simply going to put a E bar here, and I'm going to skip this subscript L. So this E bar is now the expectation value of the energy. And what we are going to look at is the expectation value of the energy at the optimal value. So we're going to make a Taylor expansion around the optimal value. So that means that we are going to make an expansion where we have this optimal energy. So this is the energy minimum. And we expand it around the value alpha, the optimal one. And this is now going to be given by the energy. And now we have the iteration n. So we have performed this iterative procedure n times. So we know the energy, this is just a constant. So it's the value we can evaluate at a given iterative parameter. And now, since these parameters in principle are vectors, So alpha, I'm going to skip the vector sign. So just to keep that in mind, I'm going to skip bold-faced or vector sign alpha. And I'm just going to let this be represented by alpha. But be aware of now that alpha is a vector which contains all the parameters, the variational parameters, which means that this energy, which is obviously a scalar, is a function of all these vectors. So it means that when I make a Taylor expansion now around a value of alpha, this optimal parameter, this contains now alpha minus this alpha of n. So this is iteration n. And I take and transpose this quantity, and then I multiply it with the gradient. And now I'm going to introduce a new notation here. So this is the gradient of the energy at iteration n. Because this gradient is calculated with this parameter alpha. I'm going to set up what these parameters are. So everything here, the reason why I'm setting up this transpose of this vector of alphas, and is because G, the gradient, is also a vector. And at the end, I just end up with a final value for the energy, which is a scalar. So this is just the inner product of the vectors alpha times the gradient. If you are just having one parameter, this is obviously just a scalar alpha, which is multiplied with the derivative with respect to alpha. But so this parameter G, which you see here, is the derivative of the gradient. And then what I'm having then is a second derivative, 1/2 of alpha hat minus the iteration n. So this is still a vector, so I transpose it. And then this is multiplied with a second derivative, this H, which is now a matrix. And this matrix is normally called the Hessian matrix. And this is also valued at the n. I'm going to set up what these quantities are. And this is again multiplied with alpha minus alpha of n. And then I have higher order terms, plus O of alpha minus alpha of n squared, cubed, and higher order terms, which then involve higher order derivatives. So let me just define these parameters. So this G of n is actually the gradient of the energy, alpha, and this is calculated for the expectation value of the energy at the value alpha n. So this is the expectation value, E of alpha of n. Or the quantity which we simply just called D of alpha. And this is the parameter E evaluated at alpha n. That's the gradient. And then this matrix H, that is a Jacobi matrix, or normally the Hessian matrix is the Hessian. Which contains the second derivatives. Contains as matrix elements the second derivatives and now I'm just going to put up these different second derivatives. So that's going to be given by a D second derivative of the expectation value of the energy. So this is going to be, just a moment. Yeah, this is the expectation value of the energy evaluated at this value n. And this is now given in terms of D of an alpha of I of D of alpha of J, where alpha I and alpha J's are vectors. And I'm skipping the vector signs here. So it means that we are taking a derivative of the specific function, and then we also need the second derivative, and that defines a matrix elements Hij. And that's why I'm setting up everything in terms of vectors and matrices. If we only have one quantity, as you have in project number 1, this is simply just a scalar. So that means that we would have a second derivative of the energy. We would then have just these scalars. So in our case, in our special case, we have only one parameter. So we have one alpha. And that means that what we end up with then is an equation which you probably have seen before. So this epsilon of alpha optimal is then going to be given by this E calculated at alpha n. And then we are going to just get alpha, the optimal value, minus the previous value from the last iteration, multiplied with D, and then we take the derivative of D alpha, calculated at alpha n, plus, and then we would have 1/2 of alpha hat minus alpha of n squared, multiplied with the second derivative of the expectation value of the energy of D alpha, and this is evaluated at alpha equal to alpha n. And that applies to this function as well. So in the special case which we have, this is now the equation which we would end up with. So we have alpha minus alpha of n, and this is cubed. And it's common now to skip the high order terms, assuming then that the higher derivatives are small and that the difference between alpha optimal and alpha n is small. So we can neglect higher order terms. And that means that the E, if we now stay with this one-dimensional case, E of alpha optimal is going to be replaced by the expectation value calculated at alpha of n plus alpha minus alpha of n, the second derivative. And now I'm going to skip the signs that it's evaluated at this specific value. That's understood that we are calculating the derivatives at these values, plus 1/2. And this is the standard equation which is used in order to derive Newton's method. So Newton's method is actually based on a Taylor expansion, where we now simply keep terms up to the second derivative. So there's nothing more mysterious than that. Now, what we can do is obviously to rewrite the equations which we have in terms of another vector. So if we look at the equations which we have been setting up now, if we think of the general form here, the general form is that of a function f of x. If we write, and x can now be a vector, just keep that in mind, where we have some constant c. So c is a constant, plus the gradient times this quantity x. So we would have the x transpose times the gradient, which I just write with a g here, plus this term which goes like a half of x transpose times a times x. So this is the general problem which we actually want to find. And if you now look at the way you can solve this, if you think of these as vectors and matrices, then what we are looking after is the derivative of d of f with respect to these vectors x equal to 0. And when we calculate the derivatives of a quantity like this one, we need to take the derivatives of vectors, or here we would have the matrix A, which does not depend on the vector x. So we would end up with a problem which looks like A times x plus this gradient, which we want to be equal to 0. Now, this gradient is obviously evaluated at a given variable alpha of n, and same with the matrix A. So we have what this leads to is that A times x is going to be given by minus the gradient, which then in turns means that x is given by the inverse of A times g. And this matrix A, in our case, is actually given by this matrix H, which is called the Hessian matrix. So the type of problem which we are going to look at mathematically is a problem which we can translate into a matrix inversion multiplied with a gradient. And then we are supposed to be able to find the optimal values. Now, our problem, however, is that this value of the Hessian matrix is something we don't want to calculate. So let's take a closer look at what we have. So this X now, the way we have defined it, is actually given by the optimal value minus this alpha of n. So I'm just plugging back these quantities which we have defined. So which means in turn that what we have now is the following. So we have alpha minus alpha of n, which is equal to this matrix minus H. So we have H. I'm going to replace A with a Hessian now, which is the second derivative of the energy with respect to the variation parameter. And this is a function which is evaluated at alpha of n. And this is multiplied with the gradients, which is also evaluated at this value alpha of n. So that means that our alpha, the optimal value, is now given in terms of, and we have to be a little bit careful because there's a minus sign here, as you can see. So X is given by minus here. So this is a minus sign. So what we're having then is that alpha, the optimal value, is given by the previous iteration minus H minus 1, this matrix, which we don't want to evaluate, and G times alpha evaluated at n. So that's the gradient or the derivative of the energy. Let me just quickly remind you of that one. This is just the gradient of the energy evaluated this parameter alpha of n. And this is given by the expectation value of the energy as a function of alpha of n. Now, what you see now is that the standard gradient descent procedure. So what this is here is actually Newton's method or Newton-Raphson's method. So this kind of iterative procedure, which we have outlined here, this is nothing but just another way of writing Newton-Raphson's methods. So let's just frame it in here. So this is where we truncated at the level of the second derivative in our case. And just keep in mind that in Newton's equation or Newton's Raphson's method, what you normally have is a function f of x, which you want to put to 0. In our case, what we want to put to 0 is actually the derivative. So when you look up in a standard textbook, when you look up Newton-Raphson's methods, you're putting this one to 0. In our case, we are taking the gradient, which we want to drive to 0. And the original function which we have started with is based on a Taylor expansion of the energy around its optimal value. And by truncating the Taylor expansion at the level of the second derivative, we can then set up a general type of problem which looks like this. And that type of problem leads to this expression, where we now replace A with the Hessian matrix, which is the second derivative of the energy. And then we can set up an iterative scheme where we have actually defined this X to be given by alpha optimal minus the previous iteration. And then we end up with the equation which you see here. Now, this is nothing but what's normally called Newton-Raphson method. But in our case, since we have this second derivative, this is for a function f of x equal to 0, which is actually given by the gradient of another function with respect to x. And we can call this function here the energy function, where x now plays the same role as alpha. So if we now accept this, that we can neglect higher derivatives of the energy, and that we can now perform this iterative procedure, What is left then for us now is actually to evaluate the Hessian matrix. So and as I said, in Monte Carlo calculation, in MC calculations, H of this alpha of n involves several multidimensional integrals. Multidimensional integrals which are evaluated stochastically. Now, obviously, this stochastic evaluation of these integrals leads to errors because we cannot afford to spend too many Monte Carlo cycles. And this means that we are actually looking for recipes which can circumvent the calculation of this Hessian matrix. For those of you familiar with machine learning algorithms, you know that this second derivative of the so-called cost function is something which we also want to avoid the evaluation of. Like if you're studying neural networks, what you typically end up with then is a set of parameters which can go into millions or even billions of parameters which you want to optimize. So the surface you want to optimize in order to find a minimum is a really, really multidimensional one. And that clearly means that this Hessian matrix will have huge dimensionalities. And at a certain point, this is just not feasible. So the simplest method, and that was the one which I implemented in the lectures here, the code which you saw, the brute force code, the simplest method, is now to replace this second derivative with a constant. Simplest method is that h calculated as a function of alpha n here is now being replaced with a constant gamma, which is a constant. And in machine learning, this is normally called, in the machine learning literature, this is normally called the learning rate. But we are just going to call it just a constant here. And that leads to a famous method, which is called the gradient descent. And you will see that there are going to be many, many types of gradient descents. So one of the simplest modification of this one is gradient descent with momentum, which we will discuss in more detail, not next week, because then we have only lab, but the week thereafter. And then in the week thereafter, we may have only lectures instead of lab. And we are going to go through these different ways of implementing these gradient methods. So the gradient descent gives us a recipe where we now have the optimal alpha, which is now given by the previous iteration, minus this parameter gamma, which we normally would put to a small value. So we could have a grid of values. So it could be given by, let's say, 10 to the minus 4, 10 to the minus 3, 10 to the minus 2. Typically, these are typical values. Clearly, the smaller you make it, the less you move. The larger you make it, the more you jump back and forth. So there's a fine-tuning of these constants, which is needed. And that leads to different schedulers where you can actually tune these parameters in a way which also includes information about the gradients. And for those of you, again, who've taken a course in machine learning, you probably heard about recipes like adaptive gradient. You've heard about the root mean square propagation and many other such ways by which you can improve the calculation of this parameter gamma. So, and this is just going to be given by the gradient now. And in our case, this is a derivative of the energy with respect to the parameters alpha. And this is going to be given by E evaluated at alpha of n. So this is the simplest possible method we can think of, and that's the one which I implemented in the lectures. And then we have other methods, which are normally called quasi-Newton methods. So where you try to approximate the calculation of the Hessian with some initial guesses, and you use these to evaluate the Hessian matrix. And this is a class of methods where this Broyden's algorithm is one of them. Broyden's algo. And we are going to discuss that one. We are going to have gradient descent with momentum, which many of you have met before. This normally speeds up the process. Momentum. And then we have all the other methods like stochastic gradient descents, etc., etc. Gradient descent. There's another method which is called stochastic reconfiguration, which we're also going to discuss. Reconfiguration, which has been used in standard variational Monte Carlo calculations, but it's also very useful when we are implementing neural networks and calculations of these gradients. And there are other methods like the steepest descent or conjugate gradient descent methods, but the conjugate gradient method and the steepest descent, they actually rely on us being able to evaluate the second derivative of the energy with respect to the variational parameters alpha. So this is the, today was meant to give you the kind of overarching view, and the whole, how to say, the theme now rotates around us being able to find the optimal parameters with as few cycles as possible so that we can find the optimal values of the parameters. And from there, we mount the large scale Monte Carlo calculation where we try to get the best possible statistics by simply adding as many Monte Carlo cycles, which we are able to do and which we are willing to spend. So number of Monte Carlo cycles means that you have to spend a certain number of CPU hours, and the number of CPU hours you have accessible depends on how much you have as a quota on national supercomputing facilities. So the layout of what is going to come now is more about refinements of what we have so that we have an efficient machinery which allows us to tackle multidimensional problems. Okay. This is basically where I want to stop today, and that sets the scene for the next set of lectures, which will then deal with these type of methods here.